Today we will discuss section 3.2, innovation sequences. So the word innovation means something new. So we have the measured output from the system. That will be the V from V1 until Vk. Suppose we have V1 until Vj minus 1. When we receive a new measurement, Vj, then we say it is a new measurement. But this is not what we mean innovation. Innovation, we mean some new information. That is the information that's Vj consists, that part is not included in V1 until Vj minus 1. That will be Zj. So the innovation sequence Vj contains the part of Vj that is not carried out in V1 until Vj minus 1. If I draw a graph, suppose this is Vj. So if we decompose Vj to this space, is the space spanned by all V1, Vj minus 1. Then this vector is Zj. We can see that the Zj is orthogonal to all the vectors, the linear combination of V1 until Vj minus 1. And it can be constructed in this way. So the Zj is Vj minus Cj and y hat j minus 1. We assume y hat minus 1 is 0. So Vj is a measurement, and Cj is the observation matrix in 3.1. That's the Cj here. Then y hat j minus 1 is a linear combination. It's a matrix. The matrix times the Vi. Vi is from V0 until Vj minus 1. Then what is the matrix P height? So P height are chosen so that, y height j minus 1 solves the minimization problem 3.2, but with the W0 until WR replaced by V0 and Vj minus 1. So 3.2 is this minimization problem. We just replaced, we found the best estimate of Sk from a space. It's not, here is V0 until Vj minus 1. So in this way, we can also see that Vj actually is a linear function. The Zj is a linear function of V0 until Vj. Then to get Zj, it requires an orthogonalization process. Now we have this correlation properties of innovation sequence. The innovation sequence Zj of Vj satisfies the following property. If J is not the same with L, then the covariance between Zj and Zl is 0. That means Zj and Zl are uncorrelated. They're uncorrelated. So if they are uncorrelated, so we know this process Zj is a white process. So we can also call the process to construct Zj is called whitening. When you look at the process Vj is not a white process, but Zj is a white process. When J is the same with L, then we can calculate the covariance matrix. The variance, when they are same, is the variance of ZL. It's based on this state space description. So the R is a variance of EK. The CK is observation matrix. So the variance of ZL is RL, is the variance of the observation noise. Then we times CL is the observation matrix, and CL transpose. So in between is the covariance of XL minus height L minus 1. So I will not discuss the proof. Let's go to the last part of this section. We know the Rj is a positive definite matrix. Then the process Zj is an orthogonal sequence of non-zero vectors. So we can normalize the process Zj by using this matrix. This is the variance of the matrix Zj using the inverse of this matrix. So this is a vector. Zj is a vector, so Ej is a vector. So for the process Ej, it is an orthogonal sequence. Basically means if Ei and Ej, if I is not same with J, so the covariance between them is 0. So if they are the same, so the covariance between them is identity matrix. Then we know that the space generated by V0 to Vk is the same with the space generated by E0 to Ek. If I draw a graph to show the relationship, we have the measurement noise. The measurement is not measurement noise. Vj process, then we can use the causal linear transformation. linear operator to get the sequence of Zj. So this is a linear operator because of the height y minus 1 is 0. If height y minus 1 is not 0, it's not a linear operator. It is a affine operator. Then we can go back from Zj, we can construct Vj process by using causal linear inverse. Then from Zj, we can construct process Ej. Ej is also a wide process, and it's normalized. The variance is identity matrix. So here we use some normalization.